will continue from where we stopped in our discussions on Newton's laws of viscosity. We had earlier mentioned that viscosity is the amount of resistance shown by different fluids. And I remember we talked about this equation where this symbol represents tau and this S represents stress. And this symbol actually, apart from representing tau, which is called shear stress. So tau S represents shear stress, and it is equal to minus mu. This symbol is mu, where mu represents our viscosity. And then we have dv dy. This represents our velocity gradient. And then we have n, which is the power of this equation here. So this equation represents an important equation that we are going to work with as we move on. This is the equation of shear stress. So this equation represents Newton's law of viscosity used to model momentum transfer. Solid materials do not satisfy this equation, so we label it equation A. Solid materials do not satisfy this equation. Only fluids such as liquids and gases satisfy this equation. In this equation, if n is equal to 1, the fluid is Newtonian in nature. But if n is not equal to 1, then the fluid is not Newtonian. So we can plot a graph. Since we know we are familiar with this equation, we can therefore go ahead and plot a graph for Newtonian and non-Newtonian fluid. If we do that, in the case where n is equal to 1, it means we are going to have a straight line equation. So this is exactly what you're going to have here. For all the values of the shear stress that we have on the horizontal axis, we are going to obtain a value of dv dy, the velocity gradient. Okay, so starting from shear stress equal to 0 right up until any value we decide, we can obtain the value of velocity gradient dv dy, and then we'll plot that graph of dv dy against shear stress. If we do that for n equal to 1, we will obtain a straight line for the Newtonian fluid. And in that particular case, the slope is going to be equal to 1 over mu, when mu is our viscosity. Okay? For an ideal fluid, our mu is equal to 0, the viscosity is equal to 0. And then when you look at this parabolic shape here, you will find out that this is a non-Newtonian graph. When we have a parabolic shape, it means it is not linear, hence it is non-Newtonian. In that case, our n is not equal to 1. So for all the values of the shear stress, which is measured in Pascal, the shear stress is measured in Pascal. For all the value of the shear stress, we are going to obtain certain values for the velocity gradient when n is not equal to 1. And when we plot the graph of those values, we would obtain a parabolic shape for non-Newtonian fluid. We should pay attention to this fact. Gases and thin liquids are Newtonian in nature. That means for gases and liquids, their n is equal to 1. We mentioned that earlier. Thick, long-chained hydrocarbons are usually non-Newtonian in nature. Also, we have force over area. This Fs represents the shear force. Force over area is normally given as pressure. So when we have shear force over area, we have what we refer to as our shear stress. And don't forget that shear stress is also measured in Pascal, the same unit as pressure. And that shear stress is given as minus mu dv dy for Newtonian fluid. If you arrange this equation, you will discover that dv dy is equal to 1 over mu multiplied by tau s. This tau s represents our horizontal axis, and then this dv dy represents our y-axis. This 1 over mu will represent our gradient when we consider the y equal to mx plus c, which is our straight line equation in mathematics, for some of us who are still familiar with our mathematics. All right. Fs should always be the applied shear force parallel to the fluid motion. So what we have, when you look at this diagram here, you can see we have our velocity gradient. You can see we have these molecules here. These are representing the speed. You can see we have a fluid in motion moving in this direction, in the forward direction, and then you can see we have the resistance which will be moving in the opposite direction. The fluid is moving in the forward motion. The resistance is going to be moving in the opposite direction because resistance is trying to stop the fluid from moving. So this is exactly what this diagram represents. And what you see here represents the speed of the molecule. What you see right at the top here represents the speed of the molecule. And then this is the velocity gradient. As you can see, this is our velocity gradient, especially when we are dealing with Newtonian fluid. When we are dealing with non-Newtonian fluid, the velocity gradient will be a curve like this. When we are dealing with non-Newtonian fluid, the velocity gradient will be a curve. But now that we are dealing with Newtonian fluid, the velocity gradient is a straight line. What we have right at the top here is a plate, and then what we have at the bottom is another plate. What we have at the bottom is a fixed plate, and right at the top is a variable plate, as we mentioned in the first lesson that we discussed, the lesson we discussed before this lesson. You can go watch that video and pay attention to that lesson so you can get the best out of all the explanations we gave. All right, so again, our tau s, which is a shear stress, is equal to minus mu dv the y raised to power n. You know, this is our velocity gradient, this is our viscosity, this is our shear stress, and then this is our n, where n is equal to 1. We have a Newtonian fluid, and then this is exactly what we do have. All right, this can be written as change in v divided by change in y, which is equal to minus mu v top minus v bottom divided by h. Delta y is actually our h, the height that we know, and then we know that delta v would be the difference in the speed, the difference in the velocities. This is the velocity at the bottom, which is usually fixed. This is the velocity of the plate at the bottom, which is usually fixed, and then this is the velocity of the plate right at the top. Okay, the velocity at the bottom is fixed, and if it's at the origin, it means it is equal to 0. And in that case, we have v bottom eliminated. What we are left with is minus mu multiplied by the v top divided by h. H is the gap between the two plates. H is always the gap between the two plates, the allowance between the fixed plate and the variable plate. And as you can see, mu minus mu here, this mu here is constant, is the viscosity, it's constant for the fluid. And this v top over h becomes the slope of velocity profile line. This represents a situation where our h is very small. When h is very small, that is when our dv dy can be said to be constant. If h is not small, then dv dy is not constant. So we're going to have a parabolic profile when h is not small. So you can see we have a parabolic nature here. The forward movement represents the direction of flow of the fluid, and then this will represent the direction of resistance to the flow of the fluid in a parabolic shape. Here, dv dy is small at the top, and then dv dy is high right at the bottom. Highest resistance is at the bottom when dv dy is at maximum. Okay, dv dy represents our velocity gradient. When it is high, we have the highest resistance, and then when it is small, we have the lowest resistance. Please pay attention to this analysis so you can understand exactly how to put all of these contents together. Let's briefly have a quick recap. For an ideal fluid, the viscosity is equal to 0. That means there is no resistance to the flow of the fluid. So you can see mu is equal to 0. If the viscosity of the fluid is low, the fluid will move easily as a result of applied shear force. If the viscosity of the fluid is high, fluid will move slowly. At that particular point, the resistance is going to be high, and this is as a result of the applied shear force. It will move slowly as a result of the applied shear force. And in this case, we can say that the resistance is very high. When viscosity is equal to 0, it simply means the shear force on that particular fluid is equal to 0. Tau is equal to 0 when viscosity is equal to 0. Let's briefly reevaluate the unit of viscosity. Tau is equal to mu divided y. If we rearrange, we have mu equal to tau divided by velocity gradient, which is divided y, and that gives us Pascal divided by per seconds, and that gives us Pascal second. So viscosity can be measured in Pascal second. Okay, and Pascal is our pressure, which is force over area, and that's Newton per square meters multiplied by seconds. The seconds we already have here. And that will give us kilogram meters, because we know our force, our Newton is force, and force is usually equal to mass times acceleration. That is our force. Our mass is kilogram, our acceleration is meters per second squared. So you can see we have mass kilogram meters per second squared representing the force, multiplied by 1 over m squared that we already have here, multiplied by the seconds that we do have here. So 1 second here will cancel one of the seconds here. This meter will cancel one of the meters here. So we are left with kilogram per meter per second. Okay. We can say our viscosity mu is equal to 1 gram per centimeter per second, which is equal to 1 poise, or we can say it is equal to 1 Pascal second, which is equal to 1 kilogram per meter per second, which is equal to 10 poise. It is important to note that for gases, if temperature increases, viscosity of gas will increase, and for liquids, if temperature increases, viscosity of liquid will decrease. Now we'll briefly talk about the kinematic viscosity. The kinematic viscosity is represented with this symbol, and it is usually given as the viscosity we know divided by the density of the material. Kinematic viscosity is generally used in the dimensionless parameter, and in this case we take into account the Reynolds number. So as you can see we can have the dimensions of the kinematic viscosity given as follows, or the units derived as follows. You can see we have the normal viscosity, kilogram per meter dot seconds, divided by the density of the material, and if you eliminate the common terms, what you have left is meters squared per second or centimeters squared per second. So kinematic viscosity is measured as meters squared per second or centimeters squared per second. And what you see here is our viscosity. So our normal viscosity can be referred to as dynamic viscosity or absolute viscosity. And if you cross multiply, what you have is the kinematic viscosity multiplied by density gives us the dynamic or absolute viscosity. Gases are very compressible. Quantify the compressibility of gases, we can use PV equal to nRT. And don't forget, we said this is an equation that represents the ideal gas law, where P is our pressure, V is the volume, our R is the gas constant, T is the temperature, and N is the number of moles or amount of substance. The liquid compressibility is expressed by bulk modulus of elasticity, K. So we represent bulk modulus of elasticity with the symbol K, and that is given as minus dP divided by dV naught. Okay, so if you look at that and rewrite that in terms of limits, we have minus delta P divided by delta V divided by V naught. Delta P is positive, delta V is negative. Now, the bulk modulus of elasticity is an important subject, and it is defined as the increase in the applied pressure per percentage decrease in volume. So you can see we have dV divided by V naught. V naught represents the volume, dV represents change in V, which represents either a decrease or an increase. And since we already said that dV is negative, so we're talking about decrease in volume. So you can see we have decrease in volume per unit of the initial volume. The note here shows that we are talking about the initial volume, and this can be written as percentage decrease in volume as given in the definition here. Now, compressibility is the inverse of the bulk modulus of elasticity. That is why we are giving it as 1 over K. Compressibility is equal to 1 over K, and that's going to be the inverse of what we have as our bulk modulus of elasticity. We had mentioned earlier that bulk modulus of elasticity is equal to delta P. In terms of limit, is equal to delta P divided by change in V over V. The negative of change in V is because we're talking about a decrease in volume. So eventually, compressibility gives us exactly the inverse of bulk modulus of elasticity, and this is referred to as the percentage decrease in volume per unit increase in the applied force. Don't forget that pressure is simply force over area, force divided by area. There is a simple question we can easily evaluate together here. The increase in pressure applied on 1 cubic meter water is 0.1 megapascal. Given 2.2 times 10 raised to the power 9 pascal, find decrease in volume of water in cubic centimeters. So the first thing we want to do is to convert 0 megapascal into a unit we understand, and that's going to be 0.1 times 10 raised to the power 6 pascal. Mega represents 10 raised to the power 6, and that's going to be equal to 1 times 10 raised to the power 5 if you mathematically eliminate this decimal point. And that gives us 100,000 pascal. That's what we have here. So we can then go ahead and make some conversions if we want. We can then go ahead and make some conversions, which we'll make very soon. Okay, we know V naught to be 1 cubic meters as given in the question. Our delta P will be equal to 0.1 megapascal, which we have found out to be 100,000 or 1 times 10 raised to the power 5 pascal. Okay, as given in the question too. So what we are looking for, this K watt represents our bulk modulus of elasticity, which is going to be equal to minus delta P divided by change in volume divided by initial volume. If you then rearrange this expression, our change in volume over initial volume would be equal to minus delta P divided by the bulk modulus of elasticity. This therefore will give us the following expression. We know that our change in pressure as given in the question is 0.1 times 10 raised to the power 6 pascal divided by K watt, which is the bulk modulus of elasticity as given in the question, will give us 2.2 times 10 raised to the power 9 pascal. Mathematically speaking, this gives us minus 4.5 times 10 raised to the power minus 5. This minus is from this minus that we have here, and that's also the minus here, and that's exactly why we have minus 4.5 times 10 raised to the power minus 5 here after carrying out this division. Hence, we can find our change in V. Since we know our initial volume to be 1 cubic meters, we just cross multiply. So change in V will be equal to minus 4.5 times 10 raised to the power minus 5 multiplied by 1 cubic meters. So when you multiply this out, what you eventually come up with is minus 45 cubic centimeters. When you convert, you can convert cubic meters to cubic centimeters. The question says we should find the volume of water in centimeters. Hence, we can convert these cubic meters to cubic centimeters. If you do that, this is exactly what you're going to have. Okay, 1 meter is equal to 100 centimeters. So 1 cubic meters will be equal to 100 centimeters raised to power 3. Okay, and so this is exactly what you have. 1 cubic meters will give us 10 raised to power 6 cubic centimeters. Hence, you can replace this with 10 raised to power 6 cubic centimeters, and you end up with minus 45 cubic centimeters as our change in V. This is mathematics. Everything going on here is just simple mathematics. So get familiar with these conversions and be able to apply them accordingly to any questions that you're dealing with. Again, please pay attention to this K watt. This represents K of water. This WAT represents water. That's why this is bulk modulus of elasticity of water. That's exactly what this kW represents. So don't get confused with that. Here is another question we can quickly evaluate together. For a pressure increase of 1 atmosphere, what is the ratio of the change in volume with respect to the initial volume? We are looking for ratio of change in volume with respect to initial volume. So that means we're looking for change in V divided by V naught. This is exactly what we're looking for. All right. So we have the bulk modulus of elasticity. We have the bulk modulus of elasticity as 2.2 times 10 raised to power 9 Pascal. We have change in pressure is 1 atmosphere as given, and then we do know that 1 atmosphere is 101,325 Pascal, and this is approximately 10 raised to power 5 Pascal. Let's go back to this equation that we know. We have already identified with this equation. The V naught equal to minus delta P divided by bulk modulus of water, and that will give us minus 10 raised to power 5 Pascal divided by 2.2 times 10 raised to power 9 Pascal. If you do that, we are going to obtain minus 4.5 times 10 raised to power minus 5 multiplied by 100%. We are converting this to percentage. That is why we are multiplying this by 100, because by the way, we're looking for a ratio. So this gives us minus 4.5 times 10 raised to power minus 3%, and that is minus 0.0045%. 1 atmosphere is equal to 101,325 Pascal. This is approximately 10 raised to power 5. There is a big part of the question which says to increase the density of water in the ratio of 0.01, what is the amount of pressure needed? What you can see here is the initial density, and what you can see here is change in density. So the ratio of change in density with respect to the initial density is given as 0.01. That is what this first statement here represents. Okay, so what is the amount of pressure needed? We do know that density is equal to mass over volume. Mass will be equal to density multiplied by volume. Okay, so if you take the differential of these, in other words, differentiate mass equal to density multiplied by volume. If you remember your laws of differentiation, this is going to be differentiation by product. So this is, you're going to use product rule here, product rule to differentiate these. Okay, so dm will be equal to, you keep density constant, differentiate V, you have dV, plus keep V constant, differentiate density, you have d density here. All right, so that's what we're going to have. If we pick that up, if we have these, you can see then we have the m equal to that, which is exactly what we have here. Hence delta m, if you consider the limits, our delta m therefore will be equal to density multiplied by delta V plus volume multiplied by delta density. When we are considering compression in a closed system, delta m is going to be equal to 0. Hence, we can say that this entire expression we have on the right hand side is equal to 0, and that's exactly what is here. If you rearrange that, you can have what we do have here. Don't forget, what we're actually looking for is the ratio of the change in density with respect to the initial density, so we can easily find that here. This is going to be the ratio, this is going to be V multiplied by density. This is delta density. There is a mistake here. This is supposed to be delta density, not delta P. This is delta density. So if you rearrange these and make delta density divided by density the subject of the formula, it will be equal to delta density over density equal to delta V over V. If you just carry out this rearrangement here, you're going to obtain these. Okay, and we do know that our delta density divided by density has been given as 0.01, so we can say that is equal to, we can then say that minus delta V over V is equal to 0.01. Don't forget, we are looking for the amount of pressure needed. We do know that bulk density of water is equal to minus delta P over the V over V naught, which is change in volume with respect to initial volume. and this will be given just as we can see here. We can rewrite it just as it is here, and that gives us 2.2 times 10 raised to the power 9 Pascal. That is our delta pressure, by the way, equal to delta P over 0.01. Where is this delta P divided by 0.01 coming from? Our minus delta V over V naught, if you look at the previous slide, minus delta V over V naught has been found to be equal to 0.01. So we just replace minus delta V over V naught here with 0.01, and that's how we got this delta P over 0.01 that we do have here, equal to our bulk modulus of elasticity of water, which is 2.2 times 10 raised to the power 9 Pascal, as given in the question that we're dealing with. Okay, so we have this expression here. If we rearrange these or just make delta P subject of the formula, because that's exactly what we're looking for, and that's the only thing missing here. You just cross multiply, and then you have your delta P is equal to this multiplied by this, and then you come up with 2.2 times 10 raised to the power 7 Pascal. If you are going to convert these to atmosphere, this will be equal to multiplied. You just multiply this by 1 atmosphere divided by 10 raised to the power 5 Pascal, and that gives us 220 atmosphere at the end of the day. Pay attention to how we made all of these conversions. This is just pure mathematics, and at the same time, pay attention to the scientific details we discussed here and how we used all of the equations that we used. So from the question which says that we should find the amount of pressure needed, that amount of pressure would be equal to 220 atmosphere. If you want, you can leave the amount of pressure at 2.2 times 10 raised to the power 7 Pascal. This is also the pressure. All we just did here was to convert Pascal to atmosphere, and that conversion is a very simple thing to do, as you can see here. Let us evaluate this example together. The velocity profile on a fixed plate is given by V equal to 0.68 y minus y squared. Now, this is not a linear equation. This is a quadratic equation, a parabolic equation, by the way. So the velocity profile on a fixed plate is given by V equal to 0.68 y minus y squared for viscous fluid. If V is the fluid velocity in meters per second and y is the vertical distance in meters, and the viscosity is 7.84 times 10 raised to the power minus 4 kilogram per meters per second, find the tau, which is a shear stress. Find the shear stress at the bottom surface and the shear stress at y equal to 0.34 meters. At the bottom surface, we had said that the plate is fixed and it's at the origin. Hence, our y is equal to 0 at the bottom surface. And then we are looking for the shear stress at y equal to 0.34 meters. Since we are dealing with a parabolic fluid, you can see here we have the flow of the fluid in forward motion, and you can see we have the resistance moving against the flow of the fluid. Alright, you can see we have a fixed plate right at the bottom, and right at the top here we have the variable plate. Again, you will see that we have, since it's parabolic, you can see here right from the beginning we had said that right at the bottom here, we had said that at the bottom the velocity gradient is usually high at the bottom, and when the velocity gradient is high, the resistance is also very high. And right at the top here, the velocity gradient is minimal, and at that particular point the resistance is 0. So you can see here we have minimal resistance right at the top here because the velocity gradient is lower at the top, and right at the bottom here it is high, and then the resistance is high. You can see the gap between the two plates is given as h, which is usually referred to as a vertical gap, and in the question it is given as 0.34 meters. That's the distance between the two plates, 0.34 meters, because we're looking for tau at this fixed point where the surface, at the bottom surface where y is equal to 0, and at the point where y is equal to 0.34 meters. So we fixed our variable plate at, we put our variable plate at y equal to 0.34 meters. Okay, so we have a parabolic velocity profile, and that is why we have this here. This is a parabola. Okay, if it were to be a linear velocity profile, it's going to be a straight line. here, and then the resistance to would be a straight line here. Okay, so we have V is equal to 0.68y minus y squared. This is a parabolic equation, and you can easily find dV dy by differentiating this parabolic equation here. If you do that, you have dV dy, and that is going to be equal to our velocity gradient. DV dy is going to be our velocity gradient. Of course, we know our V is velocity as given in the question. Hence, the differentiation of these would lead to 0.68 minus 2y. So the velocity gradient is equal to 0.68 minus 2y. We do know that our shear stress tau is given as minus mu multiplied by dV dy. We have found our dV dy, which is our velocity gradient, as 0.68 minus 2y. We multiply that by our viscosity. Again, we go ahead. We have been given our viscosity as 7.84 times 10 raised to power minus 4. If you go back to the question, we have the viscosity to be 7.84 times 10 raised to power minus 4. We bring that here, 7.84 times 10 raised to power minus 4, multiplied by 0.68 minus 2y. So we have this expression here that we can easily expand if we want to, or we can just keep it this way for use in later explanations. Now, the shear stress at the bottom surface will be equal to the shear stress at the point where y is equal to 0. At that particular point, you can replace this y with 0 or substitute 0 for y in this equation. So you have 2 multiplied by 0 here. This is deleted. This becomes 0. And then you multiply 7.84 times 10 raised to power minus 4 times 0.68. And that gives us 5.33 times 10 raised to power minus 4 Pascal. This is going to be the shear stress at the bottom surface when y is equal to 0. And then the shear stress when y is equal to 0.34, when at the point where we have our variable plate, will therefore be equal to, we are using the same equation, 7.84 times 10 raised to power minus 4 multiplied by 0.64 minus, at this particular point, you substitute 0.34 for y, and that gives us 2 times 0.34, and that's going to be 0.68. So 0.68 minus 0.68 will give us 0. So that simply means that at y equal to 0.34, our shear stress would be equal to 0. And that corresponds to the fact that when you come to the top here, we have said that at the top here, the velocity gradient is low. And when the velocity gradient is low, the resistance to the flow of fluid is very low. So at the very top here, it simply means when the resistance is low, this is where we have the lowest resistance, and that means our shear stress at that particular point is going to be equal to 0. Okay, it's approximately 0. Okay, so this means we're on the right track with our calculation. Okay, we have another question here that we can evaluate together. If a velocity of 1.5 meters per second is attained at the top plate, find the velocity gradient and the shear stress at y equal to 0 centimeters, y equal to 3.6 centimeters, y equal to 9 centimeters. So we have various gaps starting from the bottom surface right to 3.6 and to 9 centimeters. The A part says you find this velocity gradient if the velocity profile is linear. If we are dealing with a linear velocity profile, find the shear stress at these various heights. So if we are dealing with a linear profile, you can say we are going to have a linear shape here. This is the velocity gradient. This is the linear velocity gradient. And we are going to have linear resistance, as you can see here. The height or the distance or the gap between the fixed plate and the variable plate is given as h. So we're going to vary this h for 3.9 and then 3.6 and 9 centimeters. So we are looking for, we are going to evaluate a situation where our y is 0, y is 9, and y is 3.6. All right. So we have a linear velocity profile in this particular case, and this is our shear stress. This is the resistance against the flow of fluid. The flow of fluid is forward, and then this is the resistance against the flow of fluid, opposing the flow of motion of the fluid that is forward. This is backward, opposing it. we do know that our change in V divided by change in Y, delta V delta Y, equal to V top minus V bottom divided by H for a linear profile. And we do know that our V bottom is 0. When V bottom is 0, we know that we are left with V top over H, and we know this expression is a constant expression. So delta V divided by delta Y equal to V top over H. Don't forget that we had said earlier on that for a linear profile, it simply means that our n is equal to 1. One of the main conditions for having a linear profile, a linear velocity profile, is when our n is equal to 1. That means we are dealing with a Newtonian fluid. So that is why we're going to have shear stress equal to minus mu dv the y raised to power n. If n equal to 1, our shear stress will be equal to minus mu dv the y. So this is why we are using a linear velocity profile. So this is a linear velocity profile, okay, and this justifies what we are doing here. All right, so we know we have delta v delta y equal to this, and then we have this here. All right, now if we continue with what we have here, we know our v top is 1.5 according to the question, where we were told that if a velocity of 1.5 meters per second is attained, so our v top is 1.5 meters per second minus v bottom, which is 0. So we have, since we have v top over h here, we have 1.5 as our v top as stated in the question, divided by the height. We have the height, which is given as 9, because that's the maximum height. That's the maximum height that we have for the variable plate. So we have 1.5 at that very top, is velocity at that very top is 1.5, and that maximum height is what we're going to consider now. That's going to be 0.09 meters, and that gives us 16.67 if we carry out these operations. Delta V divided by delta Y is equal to 16.67 per second. Okay. This viscosity mu is given in the question as 1.96 times 10 raised to power minus 3 kilogram per meters per second. It's not written here, but it's given in the question, so please pay attention to that. Note it down. It's given in the question. Okay, so let's go ahead. We know that our shear stress is going to be equal to minus mu multiplied by delta V over delta Y, which we obtained here because we are dealing with linear velocity profile. That's what we obtained here. So we have that here, and we have found our delta V divided by delta Y as 16.67 per second. We know that our delta V over delta Y is also the same thing as V top over H, which we have already found at 16.67 here. So all we need to do is to say that our shear stress will be equal to the viscosity multiplied by our delta V over delta Y, okay, which is V top over H. All right. Before we go ahead and begin to implement that calculation, what you would find here is that the velocity gradient, since we are dealing with a linear profile, the velocity gradient at any point on the graph would be the same. The velocity gradient at any point on the graph would be the same. So this is mathematics. When we are dealing with a linear profile, we're dealing with a linear graph. Whatever you choose as your point on that particular graph, the gradient is expected to be the same. So that means that the velocity gradient at y equal to 0 will be equal to the velocity gradient at y equal to 3.6 centimeters. It will be equal to the velocity gradient at y equal to 9 centimeters. And that means all these heights would have the same velocity gradient. We can then go ahead and find the shear stress at those various heights. If the velocity gradient V top over H are the same and the viscosity of the fluid remain the same, it simply means that at all those heights the shear stress would also be the same. Okay, so what you can find out here is that the shear stress at y equal to 0 at the bottom, where we have the fixed plate, will be equal to shear stress when y is equal to 3.6 centimeters, and that will be equal to shear stress when y is equal to 9 centimeters. All right, and that will be equal to the viscosity multiplied by the V top over H, or delta V over delta Y, and we know that to be equal to 16.67. So we have V top over H at 16.67. We have the velocity gradient as 1.96 times 10 raised to the power minus 3. If you multiply that out, you would obtain 0.0326 Pascal as our shear stress. One of the things I want you to pay attention to, and I think you would have seen, is when we are implementing the value of our viscosity, we do not include this negative value. Okay, this negative value is just to show that there is a resistance going on. That is what the negative value represents. So this negative sign that you see here, like we mentioned in the video before this video, in the lesson we had before this lesson, that this negative value represents the fact that the material could be, in the case of diffusion, could be transported from the region of high concentration to lower concentration, and in this particular case it represents the fact that the fluid is experiencing resistance. That is why we have this viscosity here. So most times when we are implementing these calculations, we don't use this negative to calculate. It represents the fact that there is resistance. Okay, so that's why we don't use the negative for calculations, and we have 1.96 times 10 raised to the power minus 3 without the negative sign, multiplied by this 16.67, that gives us 0.0326 Pascal. Then there is a B part of the question that says, find the velocity gradient and of course the shear stress if the velocity profile is parabolic given by this expression. In the initial question, we were told that we should find the shear stress if the velocity profile is linear for these various heights. Now we are told in the B part to find the shear stress if the velocity profile is parabolic given by this equation. If we have this equation as V equal 1.5 minus 185 0.09 minus y all bracket squared, we can find our dv dy, which represents our velocity gradient, by differentiating this velocity, this expression. If you do that, we'll be left with, this is a constant, it becomes 0. If you differentiate these, you're going to have 2 0.09 minus y, then 2 minus 1 at the top here, the multiplied by minus 1 when you differentiate this y right in the middle. Okay, so if you still understand your differential values, you can use that to differentiate this. If you don't, please dust it and brush it up so that you can know exactly how this is differentiated. Okay, so differentiate this minus y here gives us minus 1, and you multiply that out. Eventually you are left with dv dy equals 370 multiplied by 0.09 minus y, and that represents the velocity gradient for the parabolic profile. In that case, dv dy, the velocity gradient at the top, will be the velocity gradient when y is equal to 9. At that particular point, we have the velocity gradient to be equal to 370 0.09 minus 0.09, and that gives us 0 at the end of the day. Okay, and this also supports the fact that right at the top, the shear stress or the resistance is usually approximately equal to 0, because at that particular point the velocity gradient is low at that top, and when the velocity gradient is low, the shear stress is minimal, also very low. Okay, so we have shear stress at y equal to 9 to be equal to 0. Also at 3.6, when the variable plate is at 3.6, velocity gradient, the v dy will be equal to 370 multiplied by 0.09 minus y, and y is 3.6 centimeters. Convert that to meters. We have 0.036, and that gives us 19.98 for the velocity gradient. If the velocity gradient is 19.98 at 3.6 centimeters, it means our shear stress at that level will be equal to the viscosity multiplied by the velocity gradient. The viscosity, we know that already. Multiply that by the velocity gradient, that would give us 0.039 Pascal. From here, our viscosity is 1.96 times 10 to the power minus 3. Our viscosity is 1.96 times 10 to the power minus 3. So if you bring that here, 1.96 times 10 to the power minus 3 multiplied by 19.98, it will give us 0.03 Pascal as our shear stress. Also, the velocity gradient, when y is equal to 0, would be equal to 370 multiplied by 0.09 minus 0, and that gives us 33.3. So at that point, you can see that we have the highest velocity gradient at that particular point. And don't forget, we said that when we have the highest velocity gradient, that is where we have the highest shear stress. So let's try to find out what the shear stress would be at that point. Shear stress at y equal to 0 would be the viscosity 1.96 times 10 raised to the power minus 3 multiplied by the velocity gradient, and that gives us 0.065 Pascal. At this point, where we have our highest velocity gradient is at the point where we have the highest shear stress, as you can see with this value when compared to the other two values. So that's that about this example. You need to know what you're doing here. You might want to go over this example again 1 or 2 more times so that you can understand what we are talking about, and if there are gray areas, if there are areas you think you need to brush up or you don't have sound understanding, you can ask me questions about those areas right in the comment section below, or contact me by any other means and we'll be able to solve that problem. All right. Here is where we are going to end this lesson. Please give this video a thumbs up, subscribe to this channel. I'd love to read what you think about the examples and this particular topic. Thank you, and see you in the next lesson.